So in this problem, our goal is to find all the critical points algebraically and kind of figure out what the maxes and mins of this function are. So we're given the function x to the fifth minus 5x to the fourth plus 2. So for critical points, first thing we do is we find our derivative, which is going to be 5x to the fourth minus 20x cubed. Derivative of 2 is just 0. And we set this to 0 to find all our critical points. And we can factor out a 5x cubed, which is going to leave us with x minus 4 equals 0. And we see we have critical points at 0 and 4. Now, for right now, I am also going to do it for the second derivative because I know they're going to get used later in this problem. And we have some room. The second derivative is the first derivative of the first derivative. Power rule again is going to give us 20x cubed minus 60x squared. So f double prime of x, when we set that equal to 0, we can factor out a 20x squared, which will leave us with x minus 3 equals 0. And we see that there's zeros in the second derivative at 0 and positive 3. Now we're going to use these in the next part, which wants us to find where this function's increasing, decreasing, concave up, and concave down. So I'm going to make a number line for my first derivative, f prime, and put on 0 and 4. And I'm going to make a number line for my second derivative for when I do concavity, and put on 0 and 3. Now, what we need to do is we need to test the derivative to see if it's positive or negative in each of these three intervals. So for instance, if I pick -1, I get a negative times a negative, which would be positive. If I were to put in, say, +1, I'd get a positive times a negative, which would be negative. And if I was to put in, say, a +5, I would get positive and positive, which would be positive. So from this, we get this function should be increasing up to 0, decreasing between 0 and 4, and increasing again from 4 to infinity. So increasing, we have negative infinity to 0 and 0 to 4. Decreasing, we have just the interval 0 to 4. I'm going to do the same thing on the second derivative that we did on the first, except now we're testing points in the second derivative. Again, I like using the factored form. I think it's nice and quick. A test point of -1. -1 would be positive here, negative here. So it would be negative. In between 0 and 3, perhaps a test point of 1. I would have a positive here and a negative here, so it would be negative. So we do not have an inflection point at 0 because it does not change concavity. And then from 3 to infinity, say 4, we could use a test point. We'd have positive and positive. Should be positive. So concave up would be 3 to infinity. And concave down, we have kind of an interesting situation because it doesn't change. So let's take a look at the graph so we can see what's happening. So we have x to the fifth minus 5x to the fourth plus 2. Start off in a standard window, but we're going to see there's maybe not everything we need to see as it goes way down here. So window, let's change that y min to negative 200. I know this one goes way down. So we see that this graph is in fact concave down here from negative infinity up to 3 and then goes back to concave up. So even though there's that one spot where the concavity isn't changing, we can go ahead and say negative infinity to 3. So I just wanted to take a look at that. Now, if we want the values, we want to list these as points. So we have a relative max at 0 because the function went from increasing to decreasing, and let's list it as a point. The location is 0. The value is f of 0, which is 2. We have a relative min, which is occurring at 4. And we need the function value for f of 4, so we can actually use our calculator. So I can calculate value at 4. Remember, these values are coming from the original function. We use the derivatives to find out the location, but the values come from the original function. Now, the inflection point, we've only got one, and it happens when x is 3. And again, I can bring in the calculator here. And we see it's negative 160. Alright, now we're going to use these points again with our original function, because now we're going to do absolute max and absolute min on a closed interval. So the extreme value theorem says if we have a closed bounded interval, we're guaranteed an absolute max or an absolute min, and it occurs either at a critical point or an endpoint. Now, only one of our critical points is in this interval, so we only need to check f of 0. That's the only f of 4. 4 is not in our interval. We do not need to worry about that point. F of negative 2 and f of 1. And this one has already been calculated. F of 0 was 2. F of negative 2, again, we can use the calculator here just to save a little time. Negative 110. And f of 1 is going to be negative 2. So the largest, is 2. So right there is our absolute max. Smallest is negative 110, so there's our absolute min. I'm going to change up the interval just a little bit. Negative 4 to negative 2. Now, the interesting thing here, remember our critical points were at 0 and 4. Neither of those are in our interval. So all we have to check are the endpoints. Negative 2 we've already done. It's negative 110. And we can do the same for negative 4. We get a very large negative number. So our biggest is our absolute max, and our smallest is our absolute min. So again, what we're doing there is we're applying the extreme value theorem because we're only looking at a segment of our function, not over all real numbers.